Welcome to this lesson on the method of characteristics. This is a technique for solving certain kinds of partial differential equations, and today we will explain it in full plain language first, then repeat the whole thing using standard mathematical shorthand. Here is the big idea in words. For certain first-order linear partial differential equations, there exist special curves in the xy plane called characteristic curves. Along each one of these special curves, the partial differential equation turns into a much simpler ordinary differential equation, and often the solution stays constant or changes in a very simple way as we move along that curve. Let us work through an example. We are given the equation, the partial derivative of u with respect to x, plus 2 times the partial derivative of u with respect to y equals 0. We are also given the starting information that when y equals 0, u equals x squared. The first step is to find the characteristic curves. These are the curves along which the equation simplifies. For an equation of this type, the slope of each characteristic curve, that is, dy by dx, is given by the ratio of the coefficient on the y derivative to the coefficient on the x derivative. Here that ratio is 2 divided by 1, which is simply 2. So along each characteristic curve, dy by dx equals 2. This is now an ordinary differential equation, and we can solve it directly by integrating. Integrating gives us y equals 2x plus some constant number, which we will call c. This tells us that each characteristic curve is a straight line of slope 2, and different values of the constant c give different parallel lines. Rearranging this equation, we can also write the constant as c equals y minus 2x. This quantity, y minus 2x, stays the same value along any one characteristic line. Now here is the key fact about the method of characteristics. Along each one of these lines, the solution u does not change. In other words, u only depends on which characteristic line we are on, which means u is really just some function of the constant c, that is, of the quantity y minus 2x. To find exactly what that function is, we use our starting information. We were told that when y equals 0, u equals x squared. On the line where y equals 0, our constant c equals y minus 2x, which becomes 0 minus 2x, or simply negative 2x, so x equals negative 1/2 of c. Substituting this into u equals x squared, we get u equals the quantity, negative 1/2 of c squared, which is 1/4 of c squared. Since c stands for y minus 2x, our final solution is u equals 1/4 times the quantity y minus 2x, all squared. Let us check this answer as we should always do. First, check the starting condition. Setting y equal to 0 gives u equals 1/4 times negative 2x, all squared, which is 1/4 times 4x squared, which simplifies to x squared. That matches what we were given. Second, if you work out how u changes with x and with y from this formula, and combine the partial derivative with respect to x plus 2 times the partial derivative with respect to y, everything cancels perfectly to 0, exactly as the original equation required, so our solution is confirmed correct. Now we will go through the exact same problem again, but this time using standard mathematical shorthand notation, the way it is usually written in textbooks. In shorthand, our equation is written as u sub x plus 2u sub y equals 0, with the initial condition u of x comma 0 equals x squared. The characteristic curves satisfy dy by dx equals 2, which comes directly from the coefficients in the equation. Integrating this ordinary differential equation gives y equals 2x plus c, where c is a constant of integration. Rearranging, we define the characteristic variable as c equals y minus 2x. This quantity is constant along each characteristic curve. Along the characteristics, du by dt equals 0, so u is a function of c alone. We write this as u equals f of y minus 2x. Applying the initial condition on the line y equals 0, we have c equals negative 2x, so x equals negative c over 2. Substituting into u equals x squared gives f of c equals c squared over 4. Therefore, the solution is u of x comma y equals 1/4 times the quantity y minus 2x squared. Finally, the check, differentiating u sub x equals negative the quantity y minus 2x and u sub y equals 1/2 times the quantity y minus 2x. Then u sub x plus 2u sub y equals negative the quantity y minus 2x plus the quantity y minus 2x, which equals 0, confirming the partial differential equation is satisfied, and setting y equal to 0 gives u equals x squared, confirming the initial condition too. This matches our earlier plain language result exactly.